Welcome to our comprehensive guide on safe refrigerant handling and its environmental impact. This presentation is designed for HVAC technicians, focusing on refrigerant management, environmental considerations, and safety procedures. Let's dive into the essentials of handling refrigerants responsibly. Our agenda today covers a range of topics crucial for understanding refrigerants. We'll explore their environmental impact, types and chemistry, safety protocols, recovery and management techniques, retrofitting systems, and regulations and certification. Each section is crafted to equip you with the knowledge and skills needed for safe and compliant refrigerant handling. Refrigerants, when properly contained, pose minimal environmental risk. However, if released into the atmosphere, they can cause significant harm, including ozone depletion and global warming. As HVAC professionals, it's vital to prevent refrigerant emissions through regular leak detection, proper handling, and compliance with regulations. Ozone depletion is a critical environmental issue caused by refrigerants. The stratospheric ozone layer protects Earth from harmful UV radiation, but chlorine atoms from refrigerants can destroy this protective shield. Understanding the mechanisms of ozone depletion helps us appreciate the importance of proper refrigerant management. Earth's atmosphere is divided into layers, each with unique characteristics. The troposphere is where most human activity occurs, while the stratosphere is where stable refrigerants can rise and affect the ozone layer. Recognizing how refrigerant releases impact these regions underscores the need for careful containment. Ozone depletion has far-reaching effects on health and the environment. It increases skin cancer rates, damages crops, and accelerates material degradation. Each decrease in stratospheric ozone corresponds to an increase in UV radiation, amplifying these harmful effects. Understanding these impacts is crucial for effective refrigerant management. The process of ozone depletion involves the breakdown of ozone molecules by chlorine atoms from refrigerants. This catalytic cycle allows even small releases of refrigerants to cause significant environmental damage. Recognizing this process highlights the importance of preventing refrigerant emissions. Ozone depletion potential, ODP, measures a substance's ability to destroy ozone. Different refrigerants have varying ODP values, indicating their destructive potential. Even refrigerants with low ODP can cause significant damage if released in large quantities, emphasizing the need for proper recovery techniques. Beyond ozone depletion, refrigerants contribute to global warming by trapping heat in the atmosphere. This greenhouse effect exacerbates climate change, making it crucial to manage refrigerant emissions. Understanding the dual impact of refrigerants on ozone and climate is key to developing sustainable practices. Global warming potential, GWP, measures how much heat a greenhouse gas traps in the atmosphere. Refrigerants with high GWP can significantly impact climate change, underscoring the importance of leak prevention and proper recovery. Managing refrigerants effectively is essential for minimizing their environmental footprint. Refrigerants are classified into different families, each with unique environmental impacts and handling requirements. Understanding these classifications helps technicians choose the right refrigerants for specific applications while minimizing environmental harm. Let's explore the different types and their characteristics. The molecular structure of refrigerants determines their properties and environmental impact. Most refrigerants originate from simple hydrocarbons, modified to suit specific applications. Understanding these structures aids in selecting refrigerants that balance performance with environmental considerations. CFCs were the first-generation refrigerants, now phased out due to their high ozone depletion potential. Despite their stability, they persist in the atmosphere for decades, causing long-term environmental damage. Understanding the legacy of CFCs helps us appreciate the need for safer alternatives. HCFCs are more reactive than CFCs, with lower ODP but still significant environmental impact. While their use is being phased out, recovery and reclamation remain essential. Understanding HCFC's properties and phase-out timeline is crucial for effective refrigerant management. HFCs are third-generation refrigerants developed as replacements for CFCs and HCFCs. They have no ozone depletion potential, but pose environmental challenges due to their high global warming potential. Understanding HFC's characteristics and applications helps technicians manage their impact effectively. HFOs represent the next generation of refrigerants, offering low ozone depletion and global warming potential. They contain hydrogen, fluorine, and carbon, with an unstable bond that breaks down quickly. Understanding HFO's benefits and applications is key to advancing refrigerant technology. Hydrocarbon refrigerants offer excellent environmental credentials but pose flammability concerns. They consist of hydrogen and carbon atoms, similar to natural gases. Understanding their properties and safety considerations is crucial for effective and safe use in refrigeration systems. Certain flammable refrigerants are approved for specific applications, such as household and retail refrigeration. Understanding the regulations and safety requirements for these refrigerants ensures their safe and effective use. Let's explore the approved applications and their limitations. Handling HC refrigerants requires strict safety measures, including proper labeling and service access identification. Understanding these requirements helps technicians manage refrigerants safely and effectively, minimizing risks associated with their use. Refrigerant safety hazards include frostbite, asphyxiation, and compressor terminal venting risks. Technicians must be aware of these hazards and take appropriate precautions, including using PPE and ensuring adequate ventilation. Understanding these risks is essential for safe refrigerant handling. The refrigerant numbering system is a standardized method that uses numeric codes to convey the chemical composition of refrigerants. Each digit in the code represents specific elements, such as the number of carbon atoms, hydrogen atoms, and fluorine atoms. Halogens like chlorine and bromine are calculated by subtracting the sum of fluorine atoms from the total possible attachments. This system helps in identifying the chemical makeup of refrigerants, ensuring proper usage and safety. Refrigerant blends are categorized into 3 types: azeotropic, near-azeotropic, and zeotropic blends. Azeotropic blends behave as a single substance with no temperature glide during phase changes. Near-azeotropic blends have minimal composition change and small temperature glide, making them suitable for specific applications. Zeotropic blends, however, experience significant composition changes and larger temperature glides, requiring careful handling. Understanding these blends is crucial for selecting the right refrigerant for different systems. Refrigerant oils play a critical role in system operation, and their compatibility with refrigerants is essential. Using the wrong oil can lead to compressor failure, system inefficiency, and chemical reactions that produce acids or sludge. It's vital to follow manufacturer specifications for oil type and quantity, especially during servicing or retrofitting. Proper oil selection ensures smooth operation and longevity of refrigeration systems. Refrigeration oils come in various types, each with unique properties. Mineral oils are traditional but not compatible with HFC refrigerants. Alkyl benzene oils offer good solubility and work well with HFCs. Polyol ester oils are synthetic and highly hygroscopic, requiring careful handling. Polyalkylene glycol oils are used primarily in automotive applications. The shift towards environmentally friendly refrigerants has led to specialized lubricants that maintain system reliability and efficiency. The timeline of refrigerant regulations highlights significant milestones in environmental protection. Starting with the Montreal Protocol in 1987, efforts have been made to phase out ozone-depleting substances. The U.S. Clean Air Act amendments in 1990 further strengthened these efforts. By 2020, new equipment regulations took effect, and by 2026, complete production phase-out of certain refrigerants is expected. These regulations are crucial for reducing environmental impact and promoting sustainable practices. Refrigerant management revolves around the 3 R's: recycling, reclamation, and recovery. Recycling involves cleaning used refrigerant for reuse, while reclamation restores refrigerant to new product specifications. Recovery is the process of removing refrigerant from a system for storage or service. Proper management is not only environmentally responsible, but legally required, with penalties for improper venting. These practices ensure compliance and contribute to environmental conservation. Refrigerant recovery can be passive or active. Passive recovery relies on system pressure to remove refrigerant, while active recovery uses specialized equipment. Both methods are essential for safely handling refrigerants during servicing or disposal. Understanding these methods ensures compliance with regulations and promotes safe practices in refrigerant management. Technician certification is crucial for ensuring safe and compliant handling of refrigerants. There are 4 types of certification: Type 1 for small appliances, Type 2 for high-pressure equipment, Type 3 for low-pressure equipment, and universal certification for all types. Since 1995, technicians must pass EPA-approved tests to obtain certification, ensuring they are equipped to manage refrigerants responsibly. Refrigerant retrofitting involves converting existing systems to use alternative refrigerants. Key considerations include component compatibility, lubricant compatibility, capacity changes, pressure differences, and warranty implications. Technicians must follow manufacturer guidelines to ensure successful retrofitting. This process is essential for adapting older systems to modern refrigerants, promoting efficiency and compliance. The general retrofitting procedure involves several steps: baseline assessment, refrigerant recovery, oil management, component replacement, system preparation, new refrigerant charging, and documentation. Each step is crucial for ensuring a smooth transition to alternative refrigerants. Proper execution of these steps ensures system efficiency and compliance with environmental regulations.